guide of things to review from organic chemistry in order to prepare you for biochemistry. Organic chemistry is at the core of biochemistry, but you'll find that the classes are a lot different. In biochemistry, we focus on a smaller subset of organic chemistry, but we apply it into different situations and complicated situations involving things like tons and tons of water and enzymes and all of this great things. But at the heart, you still need to know those things like Lewis diagrams, arrow pushing, electrophilicity, nucleophilicity, substitution reactions, all that good stuff. And so here is a guide and some practice to reviewing those things in order to prepare you for your biochemistry class.
You should be able to do things including drawing Lewis structures for common elements. We'll go over what these elements are. We're talking carbon, hydrogen, phosphorus, nitrogen, sulfur, selenium, occasionally, things like that. You should be able to predict how many bonds common elements will form, know what charges they can take, and which charges they commonly take, know the periodic trends in size and electronegativity, and predict bond polarity. You should also be able to recognize implicit carbons and hydrogens. You'll find that biochemists are kind of lazy, and so we often don't draw in things like the carbons, things like the hydrogens. We use shorthand notation. You'll also see kind of hydrogens kind of can float out of nowhere seemingly because we're in a very water-rich environment. So you'll see protons kind of come and go a lot, and it might drive you a little crazy if you're used to or general chemistry where you balance everything perfectly. It's a lot less of that precise balancing in biochemistry because we just have molecules floating all around, unlike in a controlled reaction test tube. There's all sorts of things happening in a biological system, and so there's like water everywhere, there's protons everywhere. And so we often don't even know where those protons, where those water molecules, where the acid, where the base, where all of that stuff is coming from. And so we use basically just shorthand, or we kind of just, it just seems to fly out of nowhere. So hopefully things will make more sense when we get to those things. But just be aware. So you should also be able to recognize implicit lone pairs. That's another thing that we often don't draw in, but that are really important to be able to know that they're there so that you know what kind of reactivity you can have. You should also be able to draw resonance structures. So in order to do this, you're going to have to remember your arrow pushing, and I love arrow pushing. And so hopefully you do too, and hopefully you remember that when you're doing arrow pushing, you're always going to start from the electrons. You're going to start from the nucleophile, move to the electrophile when relevant, and those electrons can be as part of a bond. So if you have like a pi bond system or a lone electron or electron pair. So most commonly we're going to be dealing with electron pairs, and so when we're dealing with electron pairs, then we're going to have to use this double-headed arrow. And if we're dealing with a single electron, we're going to be using a single-headed arrow, but most of the time we're going to be talking about the movement of two electrons, and so you're going to see a lot of this double-headed arrow. Okay, you should also be able to identify and draw key functional groups and also know their like shorthand abbreviations. And importantly, you should know their common reactivity. So we're going to see the same kind of functional groups show up over and over and over. We're going to have those hydroxyls. We're going to have those carboxylic acid groups. We're going to have those amines, and you're going to be expected to know what type of reactions do they normally participate. Are they nucleophilic, electrophilic, all of that good stuff. You should also be able to interpret stereochemistry representation. So remember that when we have one of those wedges that's filled in, that's something that's coming right towards you. If you have those dashed lines, that's moving away from you. You can think of it kind of like getting faded more because it's moving away from you. And so you have those dashed lines. And if something is a straight line, it's going to be in the plane of a paper or screen. Note that a lot of times we're not going to include the stereochemistry, but sometimes you will include the stereochemistry, and we'll talk about some key times when it's important, when stereochemistry really can come into play, especially because even if we don't explicitly draw it or talk about it, the stereochemistry is going to be really, really important for things like whether a drug, say, can be processed by the body, whether it can be metabolized, whether it might be harmful or helpful in the case of some drugs like thalidomide, as well as whether or not the molecule can actually be used by enzymes, because enzymes are basically designed to bind to one stereoisomer, and if you have the other stereoisomer, well, then that wouldn't work. And so our bodies have kind of specialized in using like L-amino acids and D sugars. And so you should be able to also recognize, if we are drawing stereochemistry out, I want you to be able to recognize when we have stereoisomers. So when things are not the same, when they are different in 3D space. You should also be able to recognize nucleophiles and electrophiles. So remember, a nucleophile is something that has more electrons or electron density than it wants, and it's going to go seek out a nucleus because that's where the protons are. And it's going to seek out that nucleus in an electrophile, which is something that really, really wants some more electrons. And so we'll go over how we can review how we can predict whether something's a nucleophile and electrophile, and also go over some of the key nucleophiles and electrophiles that we'll see in biochemistry and that you'll be expected to be able to identify as a nucleophile or an electrophile. You should also be able to compare and predict the strength of the nucleophiles. And it's really important to remember that we're in an aqueous environment. So we're in a protic solvent. So we're going to have to take into effect things like the protic effects and the shielding of nucleophiles affecting their reactivity. You should also be able to, going back to this draw arrow pushing mechanisms for simple SN2 and SN1 reactions. Unlike in your organic chemistry class, we're not going to have a ton of mechanisms that you're going to need to know. But you should know the basics of SN1 and SN2 and be able to kind of draw some arrow pushing interactions. But commonly, we're going to be seeing these interactions in the context of an enzyme. And so the enzyme is going to actually be helping things out. So we can't often draw just like simple reaction diagrams like you might, or reaction mechanisms like you might see in organic chemistry, because we often have like multiple things coming into play, because we have the enzyme at the active side of the enzyme contributing some things, and another molecule contributing some things, and then maybe the water molecule come in. I mean, it's all very coordinated, but you still have that same basic ideas of that electron flowing, of having the nucleophile go and attack the electrophile. Okay, so let's start back at the very, very basics though, and go back to the elements. So hopefully you're very familiar with this periodic table. You should be able to know trends in the periodic table that we'll talk about, as well as basically how the periodic table can be used as a guide to predict how elements are made up at the subatomic level and how they might react. So basically, we have that whole periodic table, and in chemistry, you probably looked at a lot of that periodic table and you went into all of these different things about all of these different colored things, which are colored differently because there are different types of elements. So over here, say we have the metals, and then over here we have our non-metals, and then we have transition metals and all this complicated stuff. Then in organic chemistry, they simplified things, and you took out a lot of this, you took out the middle of this, and you just had some more core elements. In biochemistry, we're going to simplify things even further, and these are going to be the main ones that you're going to see. And most often, you're actually just going to be seeing hydrogen and carbon, but those are typically going to be the boring parts of the molecule. And when we have real reactivity, that's often going to be involving nitrogen, oxygen, phosphorus, or sulfur. You'll also occasionally see selenium show up, and so selenium's right under sulfur here, and we'll take a look at that later. And you might also occasionally see like iodine and silicon, but not like in like experimental setups and things like this. What's really important to know is that remember those trends in your groups. So when you're looking at something that's below something else in the periodic table, they're going to have a lot of similar properties. And this is going to be because they have the same number of valence electrons. They just have an extra shell in between those valence electrons and the nucleus. So basically, I want you to be able to draw Lewis structures for these common elements. And so remember when we're drawing a Lewis structure, that's where we're just drawing those valence electrons. And remember, those valence electrons are going to be the ones that are outermost. They're going to be farther from the positive pole of the nucleus. So they're going to be more loosely held. They're going to be more reactive. Now, for a bigger element, they're going to be even farther away, so they're going to be even more reactive because they're farther from that pole of the nucleus. And we'll talk much more about this and how it relates to an atom's nucleophilicity. But first, let's just go ahead and draw those Lewis structures. And remember that the Lewis structure of an atom is going to be the same as down a group is going to be the same. So our carbon and our silicon are going to have the same. Nitrogen and phosphorus are going to have the same. Oxygen and sulfur are going to have the same, et cetera, et cetera, et cetera. But those are going to be different from one another. So why don't you pause the video and try this for yourself? Okay, now let's fill this in. And so let's use, for this, we're just going to use purple to draw on these electrons. So let's think about carbon. How many valence electrons does carbon have? Well, it has 1, 2, 3, 4. And I said that, well, silicon is going to be the same. So we have 1, 2, 3, 4 here as well. But remember that these are going to have a whole shell of electrons in between those. And so these are going to be more loosely held, and this is going to be a bigger atom. Okay, what about this one? Well, if we're going from carbon to nitrogen, the difference is going to be a proton. And if you have the neutral form, it's also going to be an extra electron. And so when we draw nitrogen, we're going to have 5. So we have 1, 2, 3, 4, 5. And note that one of them is now in a lone pair. And we're often going to see nitrogen as having a lone pair. But that lone pair can also be involved in a bonding interaction. Okay, now let's talk about oxygen. We're going to add 1 more electron. So we have 1, 2, 3, 4, 2 of those lone pairs, and then 5, 6. And then we do the same for the second row. So 6 for that, and 5 for that. And then we're going to have, with our fluorine, we're going to have 1, 2, 3, 4, 5, 6, 7. And then we're not going to deal with this last column. So we're not going to deal with like the neon because, well, it's not going to be very reactive because it already has the full octet. So remember, we're going to be dealing with the octet rule, where basically these elements are going to want to fill this outer shell with 8 electrons. And so they're going to form bonds and give and take electrons in order to do that. Okay, so what about chlorine? This is going to be the same as our fluorine. I'm going to actually, just for simplicity, I think it's more common, we'll just draw it like that. Okay, so same sort of thing down our table because these are in the same group. So they're in the same column on that periodic table, and they're going to have similar reactivity. Oops. Sorry, I didn't know why I had the charge there, but I didn't mean to. Okay, there we go. I think I was trying to use my pointer and I accidentally used my pen. Still getting used to this. Okay, but that's what we're going to have. So in this column, we're going to have 4 valence electrons. In this column, we're going to have 5. In this column, we're going to have 6. And in this column, we're going to have 7. And this is going to impact their reactivity, because it's going to impact how many bonds they can form. And we'll take a look at that in a minute. But first, we've been talking about these. Basically, these are going to be our nonmetals. And these are going to be what we're going to be dealing with most often. We're also going to see metals, though, especially in the lab, and they're going to serve as important counter ions. They're also going to be important in our body, but we just have lower levels of them. So these are the metals that we most commonly deal with. And remember that here we're talking about the first and second columns of the periodic table. So we're looking right over here. And when we're looking at that, basically, we're going to only have a single electron in the sodium, in that shell. But if it only has a single electron, then it's going to really want to get rid of it. So instead of being a Na, what we're going to see is going to be an Na plus, because it's going to lose that electron. It's going to lose that electron in order to have a full outer shell, because remember, it has that whole shell of electrons underneath. So if it just loses that one electron, then it's going to have a full shell. It's going to be happy. So it's going to have a plus charge. And I'm actually just going to draw this in red to kind of like emphasize the difference here between that and the electrons. So we're going to have a plus charge, and then K, we're just going to have the same thing. It'll have another shell in between, but it's going to have a plus charge as well. Magnesium and calcium, well, they're going to have to lose 2 electrons in order to have an full outer shell. So we're going to see them in the form of 2+. So when you're dealing with sodium or potassium, we're going to have a +1 charge. And if we're dealing with magnesium or calcium, we're going to have a +2 charge. And this is going to come into play when we think about what they could be counter ions for. But now let's talk more about how these atoms will actually react, because remember that the reason why we care about these valence electrons is because they're going to influence how the molecules react, and they're going to react typically to form that full outer shell. If we talk about ionic bonds, what we're really just talking about are attractions. So this is what we were just talking about with, like, if you had sodium chloride, you had one sodium ion, one chloride ion, and basically each of those had given up. So the metal, the cation, had given up an electron to become positively charged, and then the chlorine in this case had taken an electron to become negatively charged. And so these atoms are often going to be, so these ones are often going to be negatively charged, because if they just gain one more electron, they'll have their full outer shell. And then they can serve as counter ions for our metals over here. And so that would be an example of an ionic bond. Basically, they swap electrons. One gives up an electron, one takes an electron. And then because they're oppositely charged, they hang out closely to each other. And so this is going to be, we call this an ionic bond, but really it's just like an attraction. And we'll also talk later about like hydrogen bonds, which again, those are just like attractions, versus actual covalent bonds when they're sharing pairs of electrons to form molecules. Okay, so why don't you go ahead and write out formulas for salts of, so salts, remember we need to balance our charges, so you have a positive and a negative that cancel out to give you a neutral compound, for potassium and sulfate, as well as for magnesium and chlorine. So why don't you go ahead and pause the video and try that out. Okay, let's go ahead and show how we do this. So for potassium, remember that we have a +1 charge. So we have a K plus. And for our sulfate, that's going to be SO4 2 minus. And so we have a -2 charge and a positive. So we have a 1+ charge, and then we have a 2 minus charge. So we're going to have 2 of the potassium per 1 of the sulfate. So we now have something like this. And remember that these are really just hanging out. So if these dissociate, then what you're going to end up with is you're going to have 2K plus SO4 2 minus. But when we draw it in the salt form, we typically don't show those charges. We just show them as neutralizing one another and having this compound. Okay, now let's look at magnesium and chlorine. So if we have magnesium, that's going to have a 2+ charge. So we have our 2 positive this time. And with our chlorine, that's going to have a -1 charge. So 1 minus. And so in this case, we're going to have 2 of our anion. So we're going to have NgCl2. And remember that if this were to dissociate, so come apart, like when you dissolve it, you would end up with Mg2 plus, and you would have 2 chlorine minus. Okay, so basically that is how we would go ahead and balance these compounds. Okay, now let's get into those covalent bonds. So remember that a single bond is 2 atoms sharing 2 electrons. A double bond is when they share 4 electrons, so in 2 pairs. And those double bonds are going to be shorter and stronger. And we also have electrons that can exist as unbonded lone pairs. And these are often going to be implied. And so we'll look at how we get some practice in figuring out where there are implicit lone pairs, because we often don't draw them, but they're often present on like oxygen and nitrogen, phosphorus and stuff like this. If we have molecules that are bonded by a single bond in a hydrocarbon, this would be, we call these alkanes. And then this would be an alkene, a double bond between 2 carbons. And then if you can also have a triple bond. We're not really going to see much in the way of triple bonds in biochemistry, but that would be an alkyne when you had those between 2 carbons in a hydrocarbon. Okay, so now let's go ahead and recognize, I want you to be able to recognize the number of bonds that can be formed by each of those common atoms that we talked about. Okay, well, if we're talking about carbon, remember that we're aiming for that octet for these. So we want 8 outer electrons. What if about carbon? So in carbon, it can have it can get an electron from another atom in each of these to make each of these a pair. So what it can do is it can donate this 1 electron to form 1, 2, 3, 4 pairs. And so can silicon. So basically these would each form 4 bonds. And note that, right, this is 4 single bonds, but you can also have things like you could have a carbon that has a double bond and 2 single bonds. You still get 1, 2, 3, 4 bonds. You can also have a carbon that is going to have 2 double bonds. And so this would be 2, 4. You still have 4 bonds formed, but you have them in the form of like a double bond. So those would all be options that you could have for carbon as well as for silicon. Okay, so what about the neon and phosphorus? Well, here, this is already a lone pair, so that's not going to be much use to us, but you can still have 1, 2, 3 bonds form with these. So 1, 2, 3. So this is going to be 4 bonds. This is going to be 3 bonds. Remember, we're still talking single bonds here. With oxygen and silicon, well, they've got 2 lone pairs that are already called for, so they can form 2 bonds. And then with these, they only have 1 available for sharing. And so these are going to form a single bond. But we often see them, remember, as being, instead of forming that single bond, they just kind of steal an electron from something else, and then we end up with an ion. So we often see them as actually having that negative charge and as having taken an electron rather than having shared an electron. One other thing to note is that although we're most commonly going to see these as forming forming these 2 bonds and 3 bonds and 4 bonds, when we're dealing with things that are below this, when we're below this row, we're going to be able to have an expanded octet. So basically what this means is we're going to be able to form more than just those 4 bonds. So if we have silicon, instead of just forming 4 bonds, we can also have it form 6 bonds. With phosphorus, it can also form 5 bonds. And with silicon, we can also have 6 bonds. And so just note that you can also have more bonds formed to these than you would predict. But that's not going to come into play that much. And what about our weirdo hydrogen? Well, hydrogen has got that single electron. It can share that electron to form a single bond. So H, you can see it as having 1 bond. You can also sometimes get weird hydrogen doing in other forms. So if hydrogen, instead of sharing it, it were to give up that electron, well, now we have a proton. So we'll often refer to this as just a proton because, well, that's all it is, because the normal form of hydrogen doesn't have any neutrons. So if it loses, it only has that proton and an electron, and then if it loses the electron, well, now it's just a proton. So we just refer to this as a proton, and we'll just often abbreviate it H plus. Know that in solution, what we're actually going to be dealing with is a hydronium ion, H3O plus. So basically this proton is going to hook up with a water molecule, not just going to be floating freely around, but we're typically just going to simplify things and write proton rather than hydronium. And we're also going to kind of be thinking that these protons can kind of just hop from place to place a lot, really, really fast. And so we're not going to worry too much about where exactly protons are coming from in a lot of different cases. Although in some cases, it will be really important to know. Okay, the other form that we can see hydrogen in is in a hydride, where it has a lone pair of electrons. And since now it has extra electron, it's going to be negatively charged, and this is going to be a hydride. And we're not going to see this sort of thing too often, but we will see protons a lot, as well as lots of times with hydrogen forming that single bond. So if we have a carbon, it's going to want to have 4 bonds. It has those 4 lone pairs. It's going to form 4 bonds. We can have that be 2 single bonds and a double bond. We can have that be 2 double bonds, or we can have that be 4 single bonds. We're pretty much only always going to see carbon as being neutral. There are occasional times when you might see carbon having a positive charge. And so that would be a carbocation. In the case of carbon having a positive charge, what that would mean was that it only had 3 electrons and it would need 4 electrons in order to be neutral. So you would have a positive charge, and this would be what we call a carbocation. For a carbon to have a negative charge, basically you would have to have a lone pair, and then 3 bonds. So in this case, what you would have is you would have 1, 2, 3, 4, 5 electrons assigned to it, but it only has 4 protons, and so this would give it a negative charge. And this would be a carbanion. But again, you would only basically see these as like reaction intermediates, and you're not going to see these in stable molecules. So if we think about our oxygen, we're going to have those 2 lone pairs. And we can also then have 2 single bonds, or we could have a double bond. And both of these would be neutral. Oxygen, we're also often going to see it in a negatively charged form. We're going to see it as this form, where basically we're going to have a single bond, but then have 3 lone pairs of electrons. Now, oxygen, remember, to be neutral, it needs to have 6 electrons assigned to it because it has 6 protons. Well, in this case, it has 1, 2, 3, 4, 5, 6, 7 assigned to it. 7 electrons that it kind of owns, and so it's going to have a negative charge. So those are going to be common ways in which you'll see oxygen are going to be in this negative charge form, where it has these 3 lone pairs, or in a neutral form in which it's either forming a single lone pair or it has 2 single bonds. What about nitrogen? So nitrogen, it has those 5 valence electrons in its neutral form because it has those 5 protons that it needs to balance out. Now, in the case of nitrogen, what we can have is now we can go ahead and we can make 3 single bonds. And in this case, we still have a neutral nitrogen with these 3 bonds. We could also have like a double bond and a single bond. And again, this would still be neutral. 1, 2, 3, 4, 5 electrons assigned to it. But what we're also often going to see nitrogen is having a positive charge. So what nitrogen can do is it can use this lone pair of electrons. So it can use that lone pair of electrons and it can go and steal a proton. And basically it just takes the proton and the proton doesn't have an electron with it. So the nitrogen needs to be the one donating both of the electrons to the bonds. So you're going to end up with something like this, where basically this nitrogen is now going to have a positive charge because it has 1, 2, 3, 4 electrons assigned to it, but it needs 5 in order to balance out those protons. So this is going to be a positively charged form, and we're going to see this show up a lot. So with nitrogen, you can have 3 bonds and be neutral. So 3 bonds, neutral. Remember when I talk about like 3 bonds, that could be a combination of single and double, or it could be 3 single bonds. And if it has 4, now it's going to be plus. 4 bonds, plus. With oxygen, if it has 2 bonds, it's going to be neutral. And if it has 1 bond, it's going to be minus. And it's going to, if it has 2 bonds, it's going to have 2 lone pairs. 2 lone pairs. And if it has a single bond, it's going to have 3 lone pairs. With nitrogen, if it has 3 bonds, it's going to have 1 lone pair. And if it has 4 bonds, it's going to have no lone pairs. No lone pairs. And this is going to mean that it's going to be less reactive. It can't react as a nucleophile if it doesn't have that lone pair of electrons in order to donate. So this is going to come into play a lot. In terms of naming, if we just have a nitrogen that's forming single bonds to either carbon or hydrogen, we're going to call this an amine group. If it has a double group, double bond, then it's called an imine. And so you might see those terms used. So now let's talk about the nature of these bonds, because although those bonds involve the sharing of electrons, they're not always fairly shared. And in fact, a lot of the time in biochemistry, we're going to be dealing with unfair sharing. So hopefully in the class, things will be as fair as possible between us. And with the grading and all of that, I aim to be as fair as possible. But when we're talking about electrons sharing, these elements don't play fair. So some elements are going to be more electronegative, and the electronegative ones, remember, are going to be the ones that are going to really hold a tight pull on those electrons. They're going to be our electron hogs. And if you have one of the atoms that's more electron negative than the other, it's going to pull electron density towards it, and you're going to end up with a molecule that is polar, or at least a bond that is polar. So more electronegative, atom is going to be, gets more electrons, and those electrons, remember, are negative, so it's going to have more negative. And normally this is going to be a partial negative charge, so we're going to be drawing it with this delta, delta minus, sorry. This is going to be a delta minus. Okay, so that's going to have a partial negative charge. And then the other thing is going to have a partial positive charge because it's having the electrons stolen from it. And when we have this uneven distribution, we call it a dipole. And so in order to help think about polarity and electronegativity, I'm going to introduce a weird analogy that I'm going to use throughout my class. So basically, I like to think about electrons as dogs, and you have a dog walker that's trying to rein in all these dogs, and the dog walker is going to be like the protons in that nucleus. And so just like because the protons have this positive charge and those electrons have those negative charge, the protons are kind of like trying to rein in those, they're attracting the electrons through that charge, kind of like a dog walker pulling on a leash. And now these electrons, these dogs are really energetic, and they're going to want to get away. They're going to want to get away from that leash, from those protons, because they want to move around as much as they can in this sort of thing. But the protons are holding them back. Now, the farther away they are from the nucleus, the harder further they are from the pole. They can't like hear those protons, can't hear that dog walker calling to it. So they're going to, those are going to be the most reactive. And the farther they are away from that nucleus, the more reactive they are. And so basically, this is why the valence electrons are more reactive than the inner shell electrons, is because they're farther away. And if they are further down in the periodic table, they're going to be even further away. But if they're closer in the periodic table, then they're going to be closer to that pole. So if you have something that is electronegative, this is like something that is really tightly held by the dog walker. The dog walker has a tight pull over them. So they're going to be farther up in the table because they're going to be closer to that nucleus. So as you go up in the periodic table, you're increasing your electronegativity. And also, however, as you go to the right of the periodic table, what's happening? Well, as you go to the right of the periodic table, you're adding protons. And remember, the protons is where that pull and power is going to come from. So now in this case, our dog walker is getting stronger. And so even if things are further away, they can still be pulled in. They have another way to kind of increase its pull over those electrons. So we end up with this trend where we have our electronegativity is going to have a trend like this. Where the most electronegative things are going to be up in this right corner. And if we look at the Pauling electronegativity values, we can see that this is the case. And so we have our trend like this. So if we're going up this way, it's because we're going to be closer to the nucleus. Because remember, this is going to be the size. And so the bigger it is, the farther away those electrons are, the harder it is for them to be pulled in. So the weaker the pull over them, the less electronegative. The closer they are, the more electronegative. And so that's why we see this trend where we're going to have more nucleophilicity as we go up. And we'll take a look at how this impacts the reactivity between sulfur and oxygen. This is going to make our thiol groups, our SH groups, a lot easier to deprotonate than our hydroxyl groups, our OH groups, because those electrons are going to be less tightly held. Okay, and then our other trend direction, we said, if we go this way, well, now we're going to be adding protons. And if we're adding protons, we're adding pulling power, and so that's going to also make it stronger. And remember, one other periodic trend we have is that as we're going to the right of the periodic table, even though we're adding protons, we're going to be getting a smaller atomic radius, because those protons, basically it means that they're able to hold those electrons closer to them. And so that's another way that we can increase that electronegativity, is we're getting this even smaller size as we go this way, as well as having them closer to the nucleus. Because of the extra shells or fewer shells. Okay, so that's going to be our trends in electronegativity. And in fact, if we look at the actual values, we'll see that we have fluorine over here with a value of 4. So it's going to be the most electronegative one we're going to be talking about. If you look at carbon, that's 2.5 with hydrogen. So hydrogen's weird. And I forgot to mention hydrogen earlier, but basically hydrogen and carbon, they differ by 0.4, but we typically just consider them as pretty similar. And so if we have a hydrocarbon, we're just going to consider a hydrocarbon having non-polar bonds. But if you talk about the difference between a carbon and a nitrogen, now we have a 0.5. We have a difference of 0.5 between nitrogen and oxygen. And if we think about oxygen and carbon, well, that's going to be a whole difference of 1. Between oxygen and hydrogen, we're going to have a whole difference of 1.4. And so those are going to be really polar bonds where the negative charge is going to be concentrated on that oxygen. Okay, so now let's do some practice. Why don't you go ahead and pause the video and try to predict the bond and molecular dipoles for these molecules. So the bond dipole would be for an individual bond, and then the overall dipole for the molecule. Okay, let's go ahead and draw those in. So let's do our bond dipoles is going to be in blue. And then we'll use green. We're going to do our molecular dipole. Okay, so let's start with the bond dipoles because we need to do this first and even in order to know if they cancel each other out. So in each case, what we're going to want to do is we're going to look and see which molecules are more electronegative than the other in the bonds. In the case of oxygen and hydrogen, we know that oxygen is going to be more electronegative, and so it's going to be pulling the electrons towards it. This means that it's going to have a bond dipole where you have it directed towards the oxygen. And so when we draw these dipoles, you're drawing it toward the arrows going towards the more electronegative one, and you have this little like partial plus left over here and a partial minus left over here, and that's in the bond. And so you have the exact same thing happening over here, and so that would be partial minus and partial plus. Now, do these add together or cancel each other out? Well, they're adding together, so we end up with a molecular dipole that is going to be like this. And so that would be our molecular dipole. And this is a very, very common polar molecule that we're going to see in biochemistry. You have like 55 molar, I think it is, of water in like water. So there's a lot of water and a lot of these molecules around to interact, which is one of the reasons why biochemistry is different than organic chemistry. Or I mean, it's different than the organic chemistry you have in organic chemistry class, is because we have water everywhere, which is often something that we're really wanting to avoid in organic chemistry. And this is going to make for some challenges if you wanted to try to do like normal organic chemistry reactions in a watery solution. But our body's solution to that is often to use enzymes to help out and to make sure that we have specificity of our reactions rather than things just kind of going off everywhere. Okay, now let's look at this molecule here. Well, we mentioned how we kind of consider carbon and hydrogen to have similar electronegativities. So we're just going to go ahead and we're just going to say this one's nonpolar. All we have are carbons and hydrogen, so it's just going to be nonpolar. Okay, now finally, this last one. Well, we can draw bond dipoles because we know that oxygen is more electronegative than carbon. So basically, we're going to have our dipole going like this, and our dipole going like this. And so we'd have these molecular dipoles, but they're canceling each other out. So these are going to cancel each other out. So we have no molecular dipole. Because they're pulling evenly in each direction, we have no molecular dipole, even though we have bond dipoles. And so here's just a summary of what we just talked about. I'm going to talk a lot about electron density. So remember, those electrons are all like floating around in this cloud, moving all around. We can't even predict exactly where they're going to be. And so we can think about more of them, like just having more of that, more of the electrons are found more commonly near the one. So you can think of like more of the cloud being pulled towards that electronegative one. We'll be talking a lot about this idea of electron density rather than individual electrons. Let's talk about how we can recognize and get practice with drawing in implicit carbons and hydrogens, as well as implicit lone pairs and implicit charges. And then we'll talk a little bit about resonance structures. So as I mentioned, biochemists, we tend to be kind of lazy sometimes. But in our defense, we get a lot of it from the organic chemists. And so instead of drawing in all those carbons and all those hydrogens, we often just draw in like a skeleton formula, skeleton format, where we're basically just representing a carbon with lines and like the intersection of lines or the ends of lines. And then we kind of say, okay, we're going to have a hydrogen everywhere that there needs to be a hydrogen in order to make carbon happy. So remember that, remember when you're trying to figure out implicit things, remember C wants 4 bonds. So H is implied where number of H needed to reach 4. So we'll take a look at what I mean by this, but basically there's H's implied everywhere in order that would make it so that carbon has 4 bonds. So if carbon has 2 bonds in the structure, like it does here, well, now you would need 2 H's there. And if it has one, just a single bond, like this carbon on the end, then it would have 3 hydrogens. And this is going to allow us to focus on those functional groups. We'll get more into the functional groups in a minute, but this is where all the excitement is going to happen. It's where we have heteroatoms, so things other than carbons and hydrogens. We introduce in our oxygens and our nitrogens and our sulfurs and all that good stuff. And then this, by drawing the skeleton format, we can kind of focus on that more exciting stuff without having all those carbons and hydrogens kind of be getting in the way. So let's practice. Why don't you go ahead and pause the video and try to recognize the implicit both lone pairs as well as the implicit hydrogens and carbons. So why don't you go ahead and draw those all out? So go ahead and pause the video and do that. Okay, so now let's go ahead and we'll take a look. So remember that every place that you have like a turn, like a kink in your skeleton formula, or any place where you have an end, that's going to be a carbon. So what we can go ahead and do is we can just go ahead and we'll say, okay, we have a carbon here and here, and we have a carbon here and here. Okay, so now let's go ahead and let's focus on the hydrogens. So if we have hydrogens on oxygen or on nitrogen, we're going to draw those. They'll be drawn in. They're not just going to make you won't be expected to know if there's a hydrogen there or not, and that would also affect like the charge. So they're going to, if hydrogen's on a heteroatom, if H on heteroatom, it will be written. If H on carbon may be implied. Okay, but so we're not going to worry about these oxygens having hydrogens. We're just going to worry about the carbons. Let's take a look at this carbon. Well, it's forming 2 single bonds and a double bond. So that's 1, 2, 3, 4. So it's happy. So it doesn't need any hydrogens. What about this carbon though? Well, it's only forming a single bond. So it's going to need 3 hydrogens. So we can go ahead and draw those in. And now we just need to focus on the lone pairs. So remember, when we're dealing with oxygen, we're going to have lone pairs, and how many we're going to have is going to depend. Okay, now let's take a look at this oxygen. So basically, we remember we're looking for that octet. And so it's going to have 4 electrons from this pair, and then so in order to have the octet, it would have 2 lone pairs of electrons. And let's think about with oxygen, we have 6 valence electrons. So 1, 2, 3, 4, 5, 6. So that's all balanced out. Those are all accounted for. This is going to be our oxygen. It's going to have those 2 lone pairs of electrons there. Okay, and what about this oxygen? Well, here, when you have an oxygen that's involved with two bonds, you're going to have two lone pairs of electrons. So 1, 2, 3, 4, 5, 6. So it's going to fill that octet by having these two lone pairs, and then a shared pair with oxygen and a shared pair with this carbon. And again, oxygen has 6 valence electrons, and we can account for all of them. 1, 2, 4 in the case, 4 in the lone pairs, as well as 1 shared each between hydrogen and carbon. So that all balances out. We don't have any charges. Now let's look at acetate. So that was acetic acid. If it deprotonates, we're going to get acetate. And we're going to be looking a lot at this throughout the course, and we'll deal more in a minute of how we can draw resonance structures for these. Okay, so when we're dealing with acetate, we're going to have the same thing over here. This oxygen is going to be the same. We're going to have the same thing with these carbons. The only thing that's differing is going to be the protonation state of this oxygen. So what happens when it deprotonates is it's going to be losing that hydrogen, but it's not going to be losing any electrons. So that hydrogen is going to be losing as a proton. So you're going to get, this is an H plus. So we're leaving as a proton. And if something is leaving as a proton, well, then it's going to be leaving behind its electron. And so this oxygen is going to have that pair of electrons left over from that shared bond. And this is how it's going to get its octet. 1, 2, 3, 4, 5, 6, and then that shared pair of electrons here, 7, 8. But because it's sharing that electron, well, now if we think about how many electrons oxygen has normally, that's 6. But right now it has 1, 2, 3, 4, 5, 6, 7. So it has an extra electron compared to its number of protons. So it's going to have a negative charge. And so that's where we get our negative charge. And since it has that negative charge, well, then we know, oh, it's got to have, it must have these 7 electrons. And so one of them is coming from the shared pair. And then the other ones of these other 3 are going to be in these lone pairs. Okay, let's do another one. And this time, I'm not going to put those charges in for you. You're going to have to figure out where there should be charges in here. So why don't you go ahead and pause the video and try this out. Okay, so let's start with those carbons. Draw those in. And now remember, we need to go and we need to see if those carbons need hydrogens. So this is just what we saw before. This carbon already has 4 bonds. It doesn't need any hydrogens. It's happy as is. This carbon has 3. So we're going to give it a hydrogen to make it 4. This one has 2. So we need to give it 2 hydrogens in order to make our 4. And this one also has 2. So we're going to need 2 hydrogens to make it our 4. Okay, this oxygens, we just talked about that. So these are going to have, this one has 3 lone pairs and a negative charge. And this one has 2 lone pairs and no charge. Okay, what about these nitrogens? So this nitrogen here, we're going to have it have 3 bonds. And when we have a nitrogen that has 3 bonds, well, this means it's also going to have that lone pair of electrons, and it's going to be neutral. This nitrogen is also forming 3 bonds. So again, we're going to have that lone pair of electrons, and it's going to be neutral. Now, what about this one? This nitrogen is forming 4 bonds. And remember that it's using its lone pair to form one of these bonds. And so in order to do this, it means it's going to be left over with a positive charge. And so this is going to be NH2, this is positive charge, and then later we'll see how we can spread this out through resonance. But this is arginine, one of the amino acids we'll talk a lot about. Oh, this one too, you have a nitrogen with this, in this form, it has an NH2 group. And so what this means is that it's going to have a lone pair of electrons. Although I should note that typically in our bodies, what we're actually going to see is we're going to see the NH3 form. So if we'll see the protonated form. And in the case of the protonated form, it used that lone pair of electrons to grab onto a proton. So this is going to have no lone pair. No lone pair. So now let's go ahead and do one more example in this case, we're looking at a different amino acid. So here we were looking at arginine, and here we're going to be looking at histidine. So I want you to do the same thing. Practice recognizing those implicit carbons, those implicit hydrogens, and identifying the formal charges on this molecule. Okay, let's go ahead and do this. So we're going to put in our carbons. All of these, we need a carbon. Okay, let's deal with our hydrogens. So this carbon is accounted for. We've seen this over and over again. This one, we have 1, 2, 3 bonds, so we're going to need 1 hydrogen. This one, we have 2 bonds, so we're going to need 2 hydrogens. This one, we have 1, 2, 3, 4, so it's good. This one, we have 1, 2, 3, so it's going to need a hydrogen. And this one, again, we have 1, 2, 3, so we're going to need a hydrogen here. Okay, so we've dealt with the carbons and hydrogens. We've dealt with the easy stuff. Now let's go over here and let's look at those oxygens. This is, again, just what we saw before. So if we have oxygen that's formed 1 bond, it's going to have 3 lone pairs, and that's going to have a negative charge. If you have an oxygen that's forming just a double bond, you're going to have 2 lone pairs, no charge. What about a nitrogen? Well, here we have a nitrogen that's forming 4 bonds. We said that if a nitrogen is forming 4 bonds, and it needs to have like to own 4 electrons in order to balance out. I mean, it needs to like own 5 electrons in order to balance out its 5 protons. And if it only has 4, now it's going to have a plus charge. So this nitrogen is going to be positively charged. And then in the case of this nitrogen, well, it's forming 1, 2, 3 bonds. We said if it forms 3 bonds, it's going to have 1 lone pair left over, and it's going to be neutral. What about this nitrogen? Well, here we have 1, 2, 3 bonds again. So we're going to have a lone pair, and it's going to be neutral. And so this would be what I would expect you to do if I was asked you to draw those like implicit things and identify formal charges. You'd be doing something like this. Okay, so now let's move on to some other concepts, including functional groups and stereochemistry. So let's talk about some key functional groups that I'm expecting you to know. These include the carbonyl group, so it was carbon double bonded to an oxygen. And you should know that in other contexts, what we call it. And so if it has a carbon on either side, we're dealing with a ketone. If it has a hydrogen on one side, we're dealing with an aldehyde. If it has a methyl group on one side, we're dealing with an acetyl group. If it has a nitrogen on one side, we're dealing with an amide. If it has an oxygen on one side and nothing after that oxygen, it's a carboxylate group. Which can give and take a proton to become carboxylic acid. So carboxylic acid is just the protonated form of carboxylate. And in our course, basically, you should know which form it's most likely to be in. And typically, that's going to be the carboxylate group. If you have if you have a carbon over here, well, now you have an ester. If you have an oxygen with carbons on either side, you have an ether. If you have an OH group, this is our hydroxyl group. Sometimes we call this an alcohol group. A nitrogen with hydrogens surrounding it is going to be an amine group. And note here that we have a positive charge on this because we have that 1, 2, 3, 4 bonds to nitrogen. And nitrogen, remember, it would need 5 electrons in order to neutralize its number of protons. And so that's an amine group, and we'll see this both in protonated and deprotonated states. A sulfhydryl group, this is basically the sulfur version of a hydroxyl group, and we can also call it a thiol group. And so we're going to be seeing this a lot as well. A couple other things, a phenyl ring is going to be basically a benzene ring attached to something. If it's a benzene and a carbon attached to something, well, then this whole thing is called a benzyl group. You don't need to worry about the benzyl too much, but you will need to know this phenyl, especially in the context of phenylalanine. It's going to help you remember that phenylalanine has a phenyl group attached to the alanine. And then note that we often represent the rest of molecules with R. So R, equals rest of molecule. Because one of the great things about functional groups is that they can act kind of like independently of the rest of the molecule in terms of when we're thinking about their interactivity, their reactivity. So we can think about core properties of these functional groups without having to think too much about the rest of the molecule, at least for when we're talking about like when you have a reaction happening, the reaction is typically happening at that one functional group, say, and the rest of the molecule might be doing really important things like helping provide the for like bonding interactions that are needed in order to position that functional part in the right place. It might also alter the pH, pKa, and all this stuff. So the other part of the molecule is important, but when we deal with a functional group, we often just want to focus on that functional group. And so we abbreviate the rest as the rest of the molecule. And sometimes you'll see it drawn as like a squiggly line or something like that. And one other that's not on here is a phosphoryl group. So basically you have a phosphorus that's going to be surrounded by oxygens. And these might be negatively charged. They can be in different charge states, but then this is going to be attached to something. And that's going to be our phosphoryl group. And we'll see that over and over and over again because it's going to be a key way in which we kind of like provide energy. So why don't you go ahead and try to pause the video and identify the key functional groups in these molecules. Okay, let's go ahead and go over these. So in this case, paracetamol, this is our Tylenol. And what do we see here? Well, we have this right here. This is going to be an acetyl group. Okay. This is going to be an amino group. And this one, oh, I guess this was a challenge because I didn't actually put this on the previous slide. I'm sorry. But this is going to be a phenol group. So this is our phenol group. When you have the benzene ring with the OH attached, that's a phenol. So this is going to be like a phenyl, and that's a phenol because we have an alcohol, and this is going to be our phenyl. So basically we have this phenol group. And this is how we get the other name, the other common name for this is going to be acetaminophen. And I actually spelled that correctly. But you can see that you get that from the acetyl amino and then the phenyl. So that would be our acetaminophen. Okay. How about this one? Pyridoxal phosphate. We're going to come across this molecule a lot in biochemistry, especially when we're dealing with amino acid metabolism. It's going to be used for transferring amino groups and things like this. What I want you to be able to recognize here is that here we have our phosphoryl group. Okay, so I'm only going to make you like actually know the ones that were in the slide before. But if you wanted to know, basically this ring, if we have a 6-membered ring with nitrogen in it, we call this a pyridine ring. Okay, and then the ones that I do expect you to know, however, so this one, this would be another alcohol. And over here, this would be an aldehyde. Okay, so that's that. Now let's talk about resonance structures. So first, let's just review what resonance is. So basically, resonance is when you have delocalized electron density in a pi bonding system. And so you have delocalized electron density in a pi system, a pi bonding system. Okay. And so this means that we're going to be involving those p orbitals. So if you remember back to general chemistry, those p orbitals, the ones that are like above and below the plane, those hourglassy type things, we're going to have these delocalized electron density. What's coolest to see is when you have it in an aromatic compound where it's kind of like in a ring. And so there you have like this density you can see above and below the ring, because you have those pi bonding, those p orbitals that are joining together in these delocalized pi bonds. In this case around a ring, but you can also have resonance that's not in a ring. It's just going to be between like molecule, like a smaller number of molecules. But basically the electrons, instead of like, although we might draw them as being on one or being on the other, we can go back and forth with our arrow pushing and show that really they could be on either form. And therefore the electron density is spread between them. And if there's charge involved, you would have the charge shared between them as well. We can represent this resonance as like a dotted line, or with resonance structures showing the different forms it could take. Note that you can often draw a lot of resonance structures. Not all resonance structures are equally important. So basically, there are ways where you can push electrons all over the place, but electrons are going to want to be, electrons are going to want to be around the more electronegative, atoms more, and so their resonance structures would contribute more. So basically, it doesn't just have to be like 50-50. But when you have resonance, you're going to have something that's kind of like in between a double bond and a single bond. So you're going to have partial double bond character. And we're going to see this is going to come up a lot when we're talking about peptide bonds. It's going to be really crucial. Another crucial thing is that because they're in that pi system, a consequence is that they have to be planar. Because they're in that pi system where you have things in above and below the plane, in order for these to merge together, they're going to have to be in a planar molecule. Okay, so why don't you go ahead and draw resonance structures involving this acetate group that we saw before. Okay, so remember that when we're doing arrow pushing, we always start from pair of electrons in this case, because arrows start from electrons or from electrons in a bond. And so in this case, we're going to start from the negative charge. But the charge is not just coming because, the arrow is not coming from the charge itself. The arrow starts from the electrons. So not just the charge symbol. Because remember, the arrows are showing the flow of electrons. So we're going to push them onto here, which means that we're going to push the electrons over to here. And so now what we're able to do is we're able to draw a structure. And remember, if we have the When we're dealing with resonance, it's going to be like a two-headed arrow. So one arrow facing each direction. And in this case, well, now this oxygen is going to have a double bond. And this oxygen is going to have a single bond. Now it's going to have those electrons were pushed up. So it's going to have a negative charge. And this one's only going to have those two lone pairs of this. And it's going to be neutral. And sorry, that diagram looks really, really funny, but these would be our resonance structures. And we could also draw things if we wanted with like partial double bonds on each of these. And then kind of like the negative charge spread throughout. So those are all valid ways to represent this. Okay, now let's do an example involving positive charge. So for this case, I just want you to focus on this part of the molecule because we just dealt with this part, and so we know this part. So let's focus on this. Focus on this part and draw the resonance structures. Okay, so one of the key things to recognize here is that we need to look and see where those implicit lone pairs are. So remember that this nitrogen is going to have a lone pair, and so is this one, because each of those is making 3 bonds, and so it's going to have a lone pair. This one, it has 4 bonds. It's not going to have a lone pair, so there's no lone pair here, but there are lone pairs here. And if we have a lone pair, well, that means that we can then push electrons. And so what we're going to do here is we're going to push electrons so that they come up onto this nitrogen. So what we can do is we can push these onto here. And if we push those onto here, then this has to get pushed onto that. And if that gets pushed onto that, what are we going to end up with? Okay, so we end up with something like this, where we have our H2N double bonded to our NH2 with lone pair, and that's still a single bond. That's going to be our NH still, and that's going to be our R. But now we see that this one, well, now this one has 4 bonds. So basically it donated that whole pair of electrons. And so now it's deficient kind of in order to neutralize its charge because it needs those 5, remember? And so what we're going to have here is this nitrogen is now going to be positively charged. This one's going to be neutral, and this one's still going to be neutral. So those would be 2 resonance structures, but we're not done. You can still push these. We haven't dealt with this nitrogen, which can now, it can donate, it can go and it push back here and push the electrons back onto here. This would give us a 3rd resonance structure. In this case, this would be back where it started from. So you would have this. This one, we didn't change. But this one, well, now what we did was we used that lone pair to form a double bond. And so it still had that hydrogen. So now it's got those 4 bonds. We're going to have a positive charge here. And so we can draw these 3 resonance structures between these molecules. And this resonance is going to be the reason why arginine is the basicity queen. So molecules really like being able to spread out charge. They don't really like charge, but they like being able to spread it out. And so if they can spread it out through that electron delocalization, well, that's great. And so this is why arginine really, really likes to be protonated and have that positive charge. So it's almost always going to be protonated when we see it in biochemistry. It has a pKa of about 12.5. Meaning that at any pH lower than 12.5, which is definitely any pH in our body, it's going to be predominantly in the protonated form. And although we typically just draw a single like resonance structure, remember that it's actually delocalized among all 3 of these. Okay, now let's talk about stereochemistry. So biochemists were often pretty lazy in our stereochemistry as well. And so we just kind of like don't worry about drawing the stereochemistry because we'd have to consider too many different Too many different arrows and it can get unwieldy and all of this various stuff, but you should be able to recognize stereochemistry and how it's drawn. So remember those wedges, those solid wedges are going to be towards you. And then the dashes are sticking away from you. Think of the signal getting farther away. And then things that are straight lines are going to be in the page. So you should be able to recognize what those represent, and then be able to tell if molecules are different from one another, if they have different stereochemistry, if the stereochemistry is drawn in. If you see some stereochemistry drawn in, then typically everything else is just implied to be in the plane. If there are some things drawn in stereochemistry, but not always. And it can get complicated. And typically we're not going to be dealing with the stereochemistry. But what I do want you to know in terms of stereochemistry is that amino acids are L. And so you would have like L-alanine or L-threonine, and all of the amino acids are chiral except for glycine. Are chiral except glycine. And then our sugars are D sugars. So you would have like D glucose and D this sort of thing. Also note that this is not levorotatory. So I know that like in organic chemistry and general chemistry or whatever, like L stood for levorotatory. And then this is not dextrorotatory. Basically for the amino acids, it's just based off of similarity to glyceraldehyde. So they figured out that glyceraldehyde, that L-glyceraldehyde, was levorotatory. And then they kind of just used if things were organized in a similar way to glyceraldehyde, then they were called L. And so the L forms of amino acids are the ones that we normally use. And similarly, in the case of the sugars, not all D sugars are dextrorotatory, but basically that's based off of the configuration, the light rotation of the simplest monosaccharide, D-glyceraldehyde. And so if things are in the same orientation as D-glyceraldehyde, then they're called D, but not all of those are dextrorotatory. So don't confuse this with like the chemistry notation. And then if we want to talk about the stereochemistry at a single location, at a single chiral site, we can use the RS notation. But we won't be using that often, but just be familiar with it. And finally, let's talk a little bit about reactivity. So when we're dealing with reactivity in biochemistry, we're often dealing with nucleophiles and electrophiles. And so you should be able to recognize these, recognize whether something be a nucleophile or electrophile, recognize if some of them would be better electrophiles than other electrophiles. And also remember that we're in an aqueous environment, so things, all that stuff that you learned about protic solvents, that goes into account. So basically a nucleophile, this is going to be something that wants to go and seek out a nucleus. So phile loves nucleus. So remember, the nucleus is where the positively charged protons are. So if we're talking about a nucleophile, well, sometimes it's going to be negatively charged, and not always, but it's going to often have like you can find a nucleophile would be like an atom with a lone pair, so it could share those electrons. This may or may not involve a charge as well. Or if you have double and triple bonds, those pi bonds, they have those kind of like extra electrons that can be donated. And so when you think about a nucleophile, think about a place where you would start your arrow. So think of place you'd start arrow pushing. And common nucleophiles that we're going to see are O minus. So we have that those lone pairs there. Sometimes we might see a nitrogen with a lone pair that can act as a nucleophile, but not a protonated one, because then we're using that lone pair to bond the proton, and then it will be taken. And then we could have our double bond or our triple bond. And so in this case, you would be moving from one of those pairs of electrons. From here, you'd be moving from the center of one of those bonds. And so those would be our common nucleophiles. So you'll often see like a hydroxyl group that gets deprotonated or something like this, and a thiol group that gets deprotonated, something like this. So we could also see if you had a sulfur, that would also be a really good nucleophile. And we'll talk about how it's actually a better nucleophile than oxygen in our bodies. Okay, in terms of an electrophile, this is going to be where arrows should end when we're doing our arrow pushing. An electrophile, they love electrons. So these ones love nucleus. That's where the protons are. These ones love electrons. And so another way I remember nucleophiles is thinking of like that lone pair on the U as kind of like a smiley face. And then with electrophiles, I like to draw a little party hat on top of an E to remind me that these are often, but not always, positively charged, or at least partially positively charged. So they're going to want some electrons to help balance out that charge. So a common place you might see this is going to be a protonated amine group, so where you actually have a plus charge. And this can get neutralized out by having electrons pushed towards it. You're often going to see the P in phosphates. So you're going to see, remember that phosphate, that phosphoryl group that we talked about? We have something like this. In this case, although we have all these negative charges, what's actually going to be happening is that this phosphate, it's having the electrons pulled away from it all these different ways. And so this is going to have a partial positive charge, and it's going to be a great electrophile. So we're going to have nucleophiles are then going to be attacking that phosphate group a lot. So we have the phosphate groups. We're also going to see carbon in a variety of different carbonyl forms, because remember that oxygen is going to be pulling electrons away from it, leaving this carbon partly positive, this oxygen partly negative. And if you have that partially negative thing, well, this is going to be a great electrophile. And so nucleophiles will be able to attack it. And then remember this, what can happen when a nucleophile attacks? You can get a substitution reaction or elimination reaction. You can get a deprotonation. So typically, if something is going to act as a if the nucleophile attacks and steals a proton, we just say it's acting as a base. But if it attacks something and kicks out something else, then we can get an elimination or a substitution reaction. And you should be familiar with both the SN1 and SN2 mechanisms. Okay. Some of the common places where we'll find nucleophiles are in the amino acids. And so we're going to be talking a lot this semester about amino acids. And these are some of the key, one of the things I want you to know about the amino acids is how they react. And the ones that are nucleophilic, well, they're going to sometimes react as nucleophiles. And so I want you to be able to recognize which ones are nucleophilic. These include hydroxyls or hydroxylates. So basically, once they lose that proton, they're going to be a lot more nucleophilic because they're going to have that negative charge. And we'll talk more in a minute about nucleophilicity trends and electronegativity trends. But basically, if they are deprotonated, if they have that negative charge, these are going to be, especially these ones are going to be more nucleophilic when they have that negative charge, because they really want that positive charge to balance it out. So where you see one of these hydroxyl groups is going to be in serine, threonine, or tyrosine. When you have a sulfothiol group, you're going to see that in cysteine. Finally, we have that amine that we talked about. And so with our amine group, we're going to find that in lysine and histidine. And note that only in the deprotonated state. So only when deprotonated. Amines only when they have a lone pair. So deprotonated. So in the case of a lysine, well, this is going to be a very small amount, and often it needs like to be in the context of an active site of an enzyme or something like this. Histidine, you'll find it deprotonated more of the time, so it's going to have that lone pair. But both of these can then act as nucleophiles. But remember that if you have this protonated, well, then this would be, if this has 4 bonds, well, now it's going to have a plus charge. It doesn't have that lone pair. It can't act as a nucleophile. So what makes things a better or worse nucleophile? As I mentioned before, the negative charge is typically going to make a molecule less happy. And if the molecule is less happy, then it's more likely to react to become happy. And the way that a nucleophile becomes happier is by finding a nucleus, by attacking another atom and finding that positive charge. And so if you make a molecule unhappier, you make it more reactive. If you add a negative charge, you make the molecule less happy, and therefore you make it more reactive. So typically the deprotonated states of things, if you have a negative charge, these are going to be more reactive. But it's not just the charge that matters, it's actually the charge density. So if that charge is spread out, then that's going to be better tolerated than if that charge is really concentrated. So the more concentrated the charge, the more it's going to be wanting to act as a nucleophile, and the more reactive it's going to be as a nucleophile. So if you spread out that charge, well, now you're going to decrease the nucleophilicity. And there are a couple of ways that you could do this. One, as we talked about, is resonance effects. So basically having that electrons, that density be shared. So in the case of a carboxylate ion, that's going to have that resonance that we looked at before. And so it's going to be happier with that negative charge than it would be than something like a hydroxyl group, that a hydroxylate ion or an alkoxide ion. Basically, this is going to have it's not going to be able to spread that out. So this is going to be more unhappy. It's going to be a stronger nucleophile than the carboxylate group. And so the carboxylate group is actually pretty happy as it is. And so it's fine having that negative charge because it likes having that resonance. And so this is going to be a happy molecule, and it's not going to act very strongly as a nucleophile. Another way that you could just spread out the charge is by having a bigger electron clouds. So remember, as you go down the periodic table, that electron cloud is getting bigger. And so basically what's going to happen is that the molecule is going to be able to spread out the charge, and it's going to be happier. And so this is going to be, it's going to be a stronger acid. If you have a bigger cloud, basically it's going to be easier to tolerate the negative charge. So typically, if we think about what I was talking about, how if you're happier with the negative charge, you're less likely to react. Well, there's also this confounding effect where when we have protic solvents, including water, which is what we're often pretty much always going to be dealing with in biochemistry, is you have this caging effect. What you're going to see is that smaller is going to be hidden. What you're going to see is that this is going to be hidden more by the water. And if it's hidden more, well, now it's less likely to react. So it's going to be less nucleophilic. So it's going to be a stronger base. So it's going to be able to take protons more readily, but it's going to be less nucleophilic. It's going to be less likely to react as just like a nucleophile. And so you can see this trend if we think about the sulfur analogs of oxygen, functional groups. So remember that would be like our thiol or thiolate. This is going to be more, the sulfhydryl group, the thiol group is going to be more acidic. And so it's going to lose that proton more easily. And then it's going to be happier in that negatively charged form. So remember that another way to think about a stronger acid is going to have a weaker base. Stronger acid has a weaker conjugate base. And a weaker acid is going to have a stronger conjugate base. And if something is a weaker base, well, it's weaker because it's happier as is. So basically what's going to happen is the sulfhydryl group is going to be a stronger acid because it has that stabler. So if you think of weaker, think stabler, more stable. It's more stable in that conjugate base form. So it's less likely to go and steal a proton. And so it's going to be happier. And what we're going to see is that we're going to have a lower pKa. So look at the pKa of a sulfhydryl group. So this is going to be a pKa of about 8.3 versus a hydroxyl group is a pKa of about 13. So this cysteine is going to be way, way, way more likely to deprotonate than a serine. And so you will commonly see cysteine be involved in reaction mechanisms. Having this lower pKa makes it so that you can activate it more easily, because remember, the activated form is much more reactive as a nucleophile when it's deprotonated. And when it's deprotonated, it's more likely than that hydroxyl group to act as a nucleophile because of the caging effect. So remember that it's going to be less hidden. So it's going to have those electrons more loosely held, and they are going to be more reactive, and they're going to be less hidden by the waters. So you're going to have this, the cysteine group be more reactive than the serine group in terms of nucleophilicity. So a thiolate is more nucleophilic than a hydroxylate, so it's more likely to act as a nucleophile. And it's more likely to deprotonate because it is going to be a stronger acid. So a bunch of different reasons why it is going to be a really great nucleophile. Some other things to take into account when determining nucleophilicity are steric hindrance. So basically, the bulkier the nucleophile, the harder it is to get in to attack the substrate, so the weaker the nucleophile. We talked about the effects of the solvent already. How basically, if you have the larger things be less trapped by water. So larger things are going to be less trapped by polar solvents, so are stronger nucleophiles. And so remember, we're going to be dealing with protic solvents, we're going to be dealing with water, and so that's going to be a key thing, is that you're going to have these be less trapped. And so they're going to be stronger nucleophiles, but they're going to be weaker bases because they can spread out the charge. We also can take into play electronegativity. So the more electronegative something is, the less willing it is to share its electrons. And if we talk about a nucleophile, well, its kind of purpose is, its goal in life is to share electrons. So if you have something that's more electronegative, then it's going to be less nucleophilic. So the more electronegative, the less nucleophilic. So nucleophilicity decreases as electronegativity increases. So more electronegative, less nucleophilic. You can think of it a couple different ways. One is that it doesn't want to share those electrons. One is that it's kind of like happier with the electrons that it has, even if it might have a negative charge, say, it wants electrons. And when we think about something that wants electrons, well, that's an electrophile. So it's kind of like the opposite of nucleophilicity. And so your nucleophilicity is going to decrease as your electronegativity increases. So in order of electronegativity, you would have like carbon be less than nitrogen, which would be less than oxygen, which would be less than fluorine. But if you think about nucleophilicity, the order is in the opposite direction. So hopefully this was helpful. Hopefully this was all just review. Just kind of wanted to let you know the things that you should focus on when you're going and reviewing your OChem, which I hope you're doing. So organic chemistry really is the core of biochemistry. But biochemistry, we only use a proportion of what you learned in organic chemistry, but we use it fundamental stuff, understanding things like nucleophilicity and electrophilicity, understanding like things like trends in your periodic table, polarity, all of that good stuff. Arrow pushing, all this stuff that you just need to make sure that you are refreshed on before you start your biochemistry course.